Hello. Um, Welcome to our workshop. So this is workshop 3, data visualization and pre-processing. Which is to say that once you gather your data, you want to work it in some way or another. Basically to create visualization so you can make some observations about what kind of data set you're working with. Um, and a lot of times data sets are not necessarily perfect. Okay. Okay. Just okay, so hello, welcome. We just wait for people to like turn up a while, like how most lectures are. Oh, beats. Hold on, Let me see. Is the sound better? Sound mic test. Everything's working. Yeah, where's our workshop? Oh yeah, should forgot to add the link to workshop 3 stuff. Hold on. Sound. Still soft. Eat. Hold on. Test, 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 test. Alright, we're good. Yeah, I guess I just have to speak louder. Yeah. Like, as in, how many people should I start? Oh, right, include melody. Sure. Hello, hello. Test, test. Can anyone see? Yeah, sorry, can anyone hear me? Or if there's any audio problem, please let me know. Alright, we're good. Alright, so maybe we should start. Okay, so guys, welcome to our workshop 3, and this has to deal with most of the time is data visualization and pre-processing. What this is once you've collected your data, which is covered last workshop, what you need to start to do is to try to observe any trends or any patterns that's involved within your data to see whether there's things you can work with, whether there's any problems, or you start to notice that maybe you're missing entries and stuff. And these are usually observed when data visualizations are used because you can start to notice that there are abnormalities or there are strange readings. From then on, what you can do is a lot of times we call it cleaning, but really is actually called pre-processing. Pre-processing deals with the measures of cleaning your data, rather to process your data so it cannot be fed into a machine learning, which we'll be covering next session. So this is really, I guess, a link up between last session and from collection to machine learning. There's a process you have to perform before you can actually achieve the most ideal results. So yeah, we'll be covering mostly three parts of this. Matplotlib is the first one I'd like to cover. It's a visualization software visualization library, my fault, sorry, that allows you to plot your data in a visualization format that allows you to that allows you to observe any changes or any abnormalities. Second part is more about cleaning. Cleaning has to do with, like what I said, dealing with missing entries, imputing data, and trying to find out what you can work with before you can feed your data into machine learning. And gaining insight is actually part of visualization, trying to figure out what your data is missing and whether there is anything you can do about that. Alright, so welcome to our workshop series. If you're here for the first time, I guess we should make an introduction of who we are and the people who are in our team. Yeah, so the head and the vice and I guess the head and the deputy head are Meredith and Evan. No, they are not dogs. They're actually year 3 computer students, and yeah, that's what they look like. So the rest of them, no, we're not cats. No, Jack's not a lion. Um, but all of us are basically members. Me, Jing Yang, and Ita, who is not here today. We're all data science students. Except I'm a year one data science student, and Jing Yang, who will be later covering some parts of your content, will be a year 3 student. And we also have Jack with us. He's a year 3 computer science student. Yay! So moving on from introduction, let's talk about why we need to do what we do in this workshop. We've gotten into data collection in last session, where they've taught you extensively how to get what you want, or rather, how do you create a data set that you are interested in once you set out to do what you need to do. And collection methods, or rather, Beautiful Soup and maybe CSV, these libraries allow you to provides you with a data set. What you need to do then from now on is that because a large amount of data can be either lost or warped in the process of these happenings, you need to look at your data, you need to inspect your data. But in case when your data has like thousands of entries, 3,000 or even 4,000 entries, you can't inspect them element by element. That would take you like forever. No, that's bad. So yeah, so what you need to do then is to plot them, or rather visualize them, so that you can have a solid glimpse at what data you have and whether they actually have a roof, have a flooring. These are things that I'll look out for. Whether your data is tail heavy, whether maybe your collection, when you look at a collection, have filtered the wrong sections and all that. So this is a time where you can actually find out what you've gotten. And third one is to find any insights, right? So why do you need to understand? So that's the question, say, why do I need to understand the data? Or rather, why do I need to fully comprehend what is going on? Why can't I just feed it into machine learning itself, since it's so good, right? No, because data sets are actually, it's not hardly perfect, it's actually never perfect. Sorry for the, not typo, but yeah, it's never perfect. You need to clean it, or rather you need to make some adjustments, you need to do some modifications to your data set in order for it to work for you. And different machine learning models actually work on different kind of data sets with different outcomes as well. So you need to understand your, not only do you need to understand your data, you also need to understand your machine learning model actually. So understanding these two allows you to, I rather modify your data set to suit your learning model better. This is also, so that will touch later on pre-processing on data, but the first thing we need to understand is that we need to understand what we need to work on. We need to understand how our data look like and whether there are anything that we should go back and collect more. Maybe sometimes you've collected a section, let's say you're collecting Grab density in Singapore. Maybe sometimes when you made a filter, you've accidentally filtered out people in the west, or rather people in the north, and that is the data set they've lost out. So this is a time when you plot your graph, when you plot your map out, you can notice that people in the west and people in the north are actually ignored. And that's when you can go back to the collection process and do more collection. So let's talk about NumPy and Pandas first. So what are NumPy and Pandas? NumPy and Pandas are two libraries that is very commonly used to create we call arrays and data frame. Arrays and data frame allows you not only to inspect the structure of the data, but it also allows you to do some modification and work with the data so it fits into certain models and types. Yep, so before you can properly visualize the data and pre-process it, we need to learn how to manipulate it because even data libraries, they have certain limitations. They require certain formats to work. So for instance, if you're using Matplotlib, you need to plot maybe with two axes, x and y, right? But maybe your data doesn't have, or it doesn't always have an x and y reading. That's why you need to start inspecting them based on NumPy and Pandas. And some of them even require you to put your rows into one list or axis. So this is when NumPy and Pandas become really useful. So like I said, NumPy contains NumPy arrays, which are basically, you can see them as a list of numbers, but the thing about NumPy is that you can have more than a list. You can have a list within a list within a list, but yeah, that's kind of complicated. For now, we just deal with simpler structures. Pandas is what we call dealing with data frames. In other words, you think about your Excel sheet. Excel sheets have rows called and columns. These are the individual indexes within your Panda data frame. It's easier for you to see in Pandas because they now create a Excel-like entry, so it's easier for you to manipulate from there on. Alright, so before we go into the visualization, let's go to our lab, so at least we get to see what Pandas look like. Hold on a moment. So, um, did we share the? Okay, sorry. So we'll be sending the links towards all the resources to you, so at least you'll get to try. For now, we'll open our workshop collab file. Sorry, it's gonna be a bit awkward. Okay, so from now on, we'll take a look at NumPy. So as usual, before we are allowed to use NumPy, we need to import it like all libraries. Yeah. So the command here, or rather the convention, is usually to always use import NumPy as NP. So next time we are calling anything regarding to NumPy, we can just call NP instead of typing out the whole NumPy. So once we run that, yep. So once we run that, it will now, Colab will basically now import NumPy into our system so we can actually access it. Hold on, so this is still initializing. Alright. So after this is ran, we'll run one more time just for good luck. Yep. So we can make 1D NumPy arrays. So what I mean by 1D NumPy array, right, is that you're creating basically a list of numbers. The simplest way you can example is to create 1, 2, 3, and 4. in the first workshop, when that's when Ita is covering a list. You can see this as a list, but a NumPy array is in its sense unique from a Python list because of the commands and the object. Because of the nature of the object itself, you can actually create. You can actually do a lot more things with NumPy arrays compared to a regular list, which we will introduce later. So for now, if we run this as so what we do right now is we create a list that is 1, 2, 3, and 4, and we store it in test list. And by doing this line, what it essentially does is it creates a NumPy array with this 1, 2, 3, 4 list. And this command dot array is basically a creator. It takes this 1, 2, 3, 4 list and turns it into a NumPy array. From there, we store this NumPy array into a variable name called test array underscore 1D. So once we run that, we will able to, once we create that, we can now have certain attributes. One of the attribute is basically like a character. So things that information regarding the NumPy array that you want to find out about. So in this case, let's say we are interested on the shape of the NumPy array, because later you find out not we can create more than just a 1D NumPy array. You can create 2D. You can create more than that. So sometimes we are interested in what our array actually look like. Think of it as a matrix. Think of it as a matrix shape and matrix size thing. So the command shape basically tells us, hey, what dimension does my NumPy array actually have? So since we created a 1D NumPy array, in other words, a one-dimensional one-line NumPy array, if we run this code, Python, or rather Colab should actually have a return result of 4, telling you that hey, this is a size length 4 NumPy array. We can also make 2D NumPy arrays. So what are 2D NumPy arrays? Like initially when you can create one row of data. So now let's say I have maybe data that's a bit more sophisticated. Data that is I want to be a bit more, let's say, complicated. Because sometimes one row of data in Excel sheet just doesn't do its job, right? So think about this as a single row in your Excel sheet. With one single row, usually you can't do much. So we want a column. So that's where 2D numpy array come about, right? So imagine here when you have each row, each each sorry uh, each individual small list here is a single row within your numpy array. So what you can do now, each individual column, my fault. So this is every single one of these is a column. Yeah, sorry, my fault. It's a row. Oops. So it's a row. So then in each individual row, there'll be 2 columns, 1 and 2. And in this second row, those will be 3 and 4. Third row is 5 and 6. Fourth row is 7 and 8. So however, you can't do this in a regular Python list because Python see list as just list, and nested list in Python is really just a list inside a list. But however, with NumPy, you can actually make this possible. You can create another NumPy array inside and store all this into a 2D NumPy array. The command is the same, so it's called np.array, and because we store this as a list of lists in Python, and in vanilla Python, it is what it is. It is just a list of lists, which is really boring. And instead, what we can do is we can create a NumPy array that is 2D in nature, so that now we have 4 rows and 2 columns each. From there on, when we run this, once again, we want to find out the shape of this NumPy array, and that's where the shape command comes in again. And if we run this again, it will return us this output. The output 4, 2 basically tells you that this NumPy array has 4 rows and 2 columns. Yeah, so think about your Excel sheet. This is 4 and 2. Yeah, so that's essentially a 2D numpy arrays. You can have more than 2 dimensions, but that would get a bit more complicated and annoying. Think of your matrices. Maybe think of 3D, 4D objects, or even 5-dimensional objects, which can get a bit dicey if you're dealing with Euclidean objects. But we try not to touch so much because this is a friendly course. Yay! So, the useful NumPy functions we are going to introduce here is actually how to create maybe a NumPy array with large size in a shorter amount of lines, I say. So yeah, there are funny commands such as numpy.once, and inside this command we call this a parameter argument. So whatever we put in this parameter is whatever attributes that Python will, or rather NumPy will take a look at it and say, oh, so you want me to create a shape that is 6. So, and the once is the command that tells Python, hey, that tells NumPy that, hey, I want to create a shape of something, rather a NumPy array of a X shape that is all ones. I think it's quite intuitive on this part. Yeah, so NumPy.once shape basically creates a NumPy array with a shape that is stated here, whatever shape that you want. You can have even 6, 4 that creates a 6 by 4 matrix that is all 1. Yeah, so that is possible within NumPy arrays. You can also create NumPy zeros. Yeah, so basically everything here is 0. Yeah, so that is. And like I said, you can create a 2D array as well. So this is an array with 5 rows and 3 columns. So yeah, so that is a shapefile tree with all zeros. That's numpy.zeros for you. And in case those who are about a bit more adventurous, as numpy random.normal. So yeah, so when life can sometimes be dicey, right? So yeah, here's the dice part. So numpy random, and random is what it says, it is any random number, right? And normal. Normal is the statistic normal as in is normal random distribution, and it has a mean 0. So this 0 stands for the mean of your normal distribution. So it should have a normal of 0 with a standard deviation of 1. Um, if I'm not wrong, these parameters can be ignored if you do not want your if you ignore the normal. But for now, we don't want our numbers to run too wild. That's why we control them between normal of 0 and standard variable of 1. The size 2 tree, as usual, is the size of our current array itself. So this in itself created another NumPy array of size 2 by 3, as stated here. But I suppose we won't be using this that much because this is a random number generator of some sort. And unless your data work which will do hopefully, please stick with us with your your project catalyst work. If some of y'all are using random number generators to do certain kind of maybe simulation work, you may want to consider random. But for now, and for analysis purposes, we won't be using this much. Just good to know. And here is a NumPy A range. So for those who are remember your for loop and range, which essentially has a format of this. Hold on, let me add the code cell. So in regular Python, for I in range 1-20 and maybe -3, we can create something else. Sorry, hold on a moment. Damn it. Okay, so for I range this, print. So what this does is, this is a standard Python format, right? This has nothing, for now this has nothing to do with our NumPy arrays. But keep in mind what this range function does. What this range function does is, hey, give me what? Give me all the numbers within the range of 1 to 20 20 not included, and for each number that you take, skip 3. And whatever number they are currently at, store it as I and print it out for me. So this is the end result of that. So what arange does, numpy arange does, is it creates a numpy array with the range of this. So with these 3 parameters, that is same as the range when you're calling the range function in Python. Except that what now numpy does is now it creates a 1D array that takes in the same range arguments as a regular Python and put it out as output. And that's how you create a numpy array of a 1D nature that has all these numbers in it. So if you notice, now we don't have a shape argument, because this shape argument, or rather the size argument, is no longer determined by is no longer, I would say, man-made by us. It's not no longer engineered by us. It is now dependent upon how long your actual whole system is. So if your system ends up being 0, 3, 6, 9, 12, 15, and 18, the shape of this is dependent on how many numbers you have between 0 and 20. There's 3 steps in between. So let's say we want to find out, let's just store this, because we want to find out some things about it. We can do that as well. So let's call this a range numpy, range array. So what we did here is just that we stored this as a ranged array. So sometimes when you do numpy work and use a range, you want to store it in a variable, but it can be hard to keep track of the size and everything. So that's why we use the shape function. So we'll write print ranged array dot shape. So from here on, we'll find out it's actually length 7. So it's 0, 3, 6, 9, 12, 15, and 18. Exactly 7 elements. Alright, so moving on from the basics of shapes and array sizes, we can now continue with vectorized operation. So think of this as your matrix operation, or rather everything that is additive, or everything that is when you're multiplying everything. So this is that. So generally, like what they say, generally most numpy mathematical functions apply on numpy arrays. We'll usually apply them like how you do vector addition, if you're familiar with the concept. But yeah, let's just take a look, and let's just start with our simple case again of an array of 1, 2, 3, and 4. Call that test array once again. So the arithmetic is really just trying to in this one is really just take this whole array, add everything by 2, or take this array minus everything by 2. This is the most classic operation that you can ever perform on any array. So it is essentially what it is. Take this plus 2, take this minus 2. Yep, for every single element, of course. So now, if you remember, the big difference between this and Python lists is that if you try this on any other Python command, um, Python will spit you back a response that say, I cannot add an integer with a list. But this is actually not the case within NumPy arrays, because when you do this operation, NumPy takes in a NumPy array, not a list. And although these two may look alike, these two are actually not the same data type. That's why you can actually perform this operation on a NumPy array and not a Python list. That's a very crucial difference. So sometimes people will get confused. So when am I dealing with a NumPy array? When am I dealing with a list? Okay, there's two ways to look at it. As in, there are two ways to resolve this problem. One is you can just type out the name of your object. For now, we'll type out test array, and you'll return you array. So any other Python list wouldn't have the array, wouldn't have the word array in front. They will only have the 1, 2, 3, and 4. Okay, maybe we should type out maybe we should give them another variable called test list, and we store them as 1, 2, 3, and 4. Yeah. Right now, if I put test array, it's array. But if I how about put test list, it would just be a regular list. So this is just a list without any word array in front. So this is one way you can tell what kind of data you're dealing with. And NumPy array always have the word array bracket with the list that you're dealing with inside. Another way to do it is rather, I guess, suppose the more straightforward way. When in doubt what kind of data type you're dealing with, not just NumPy array, in the future when you're dealing with Pandas sometimes, just write the word type inside. The type of the object is always the data type. So let's just put test array. And when we run this, it will tell us it's a numpy.nd array. So what it essentially tells you this is a numpy n-dimensional array. ND stands for n-dimensional. So yeah, this is how you know that you're dealing with a numpy array. If you're replacing this with a test list, you'll return us a list. Python is very straightforward about it. It is just a list. So when you're in doubt, when you get confused sometimes, when you're dealing with multiple data types, you don't know what to do sometimes, or rather what operations and what things, because different data types actually supports different operation types. And when you need to check whether your data type supports this, you can always use a type function to find out what you're dealing with. Alright, so once we get this over with, let's continue. So like I said, NumPy arrays can actually support a integer addition and subtraction to every single element inside its n-dimensional array. Next one we can do is actually just a vectorization. So what it essentially means is you can perform an operation on every single empty array. What we did here is we applied exponential function to every single object here. A bit excessive, but I'm just trying to make a point here. So we did a print.numpy exponent of the test array. So for every single number inside the exponential array, we put a exponent function, e to the power of 1, e to the power of 2, e to the power of 3, etc. The next one we did is a numpy.log. So it's actually a long function. So once you reduce that, it's now lon1, lon2, lon3, lon4. Yeah, so it'll return us with two arrays which already has all of these operations performed. So the general lesson within this tool is that you can perform a element in for every single you can perform an operation on every single element within a NumPy array without having to write the for loop. This is one of the biggest advantage that NumPy actually offers, because yeah, it saves a lot of typing time. Yeah, so you can, instead of just typing for every single element within a list, please do this and store it back to another list. Yeah, so usually modifying a list is actually quite a troublesome process, but with a NumPy array, this has become quite easy. Yeah, all you have to do is the operation you want to perform with the array inside. Yeah, so that's very sweet. Alright, let's talk about indexing arrays. So let's say I want to access a very specific element within my NumPy array, or even better, I want to access a whole row or whole column. You can do that. So that it can be done with indexing. Like indexing in Python, we all start with 0. Yeah, that's usually how things work. And so with the test array, we can do with a test array of this size, which is already printed out for you. So this is a 4 by 3 matrix. But the way we index is row 0, row 1, row 2, and row 3. And this is column 0, column 1, column 2. Am I following, right? Okay, so indexing basically means I want to access a specific element within this array by calling out the index of each row and column. So we kind of made the mistake of already giving you the answers, but y'all can try figuring out yourself of what test array 01 actually is. So test array 01 is I take test array, I take the 0 index row, which is the first row, and the first index within the first row. The index 1 is actually 2, because here, because the nature of this is 2, and the answer has been given. The second one is, if you remember still how to this blank thing, instead I'm taking everything within a list, tuple, everything. So I'm taking everything within it. So a test array 2 is I'm taking from this array, I'm taking row index number 2. And from row index number 2, I want everything. So this is 0, 1, and 2. Everything within index number 2 is actually 5, 6, and -3. Yes. So this test array is actually a very interesting one, because if you recall in Python, because of the specific way list and data structure is managed, as in when I refer to Python, like right here, I'm actually referring to vanilla Python. In vanilla Python, in order to access our 2, 4, 6, and 8 row here, in order to access our 2, 4, 6, and 8 row here, we actually have to call a for loop within this. And for each number, you have to retrieve the first element, which is, we call it first element, but it's actually index 1. It's how we get 2, 4, 6, and 8. So it will look something like for row in this array, retrieve index 1. That's how you get 2, 4, 6, and 8. But in NumPy array, this problem is actually succinctly solved, because NumPy array don't see them as a bunch of lists. It actually sees them as a structure with an array type with rows and columns. They see it as a data structure of itself. That's why we can do this. By taking test array, we take every single row. That means we're telling this is effectively your for every single row command, but in the language of indexing, this is take everything, right? So at test array, we take every single row and we access the first index 1 of each row and put it in the array for me. So that resulted in an array of 2, 4, 6, and 8. Alright, so the last one we're introducing is that we can actually slice our array very much like how we slice a regular list, except now because we have an array, you can imagine it like a cake. So we want a part of the cake that's from index 1 to 3 and 0 to 2 in terms of column. So how would that look like in a when we try to visualize it, right? So like I said, we are visualizing our entire array like a cake. So the way we think about it is, we start from index 1 on our row. This is our index 0, index 1. We want to start from index 1. And we want to cut away. We want to cut our array such that it cuts away. You want to exclude row index number 3. So essentially, you're cutting away number 3. That's what you're cutting. So you should not have index row number 3. So this is essentially this row. This is index 1, index 2. This is index 3, but we're cutting this away. We're not including it. That's why we're only talking about the 3, 4, -2, and 5, 6, -3 rows. From this array, we want to take the columns 0 to 2. In other words, we're taking everything. You're taking 0, this is 0, 1, this is 2, but we're always excluding the index 2. So we're cutting this -2 and -3 away. So we're left with 3, 4, 5, and 6, which is exactly what is here. So when you're dealing with a slice of data that you feel like, I don't want this, I don't want this. Imagine you are dealing with vanilla Python right now. This would be very, very, very troublesome actually. because slicing a data based on a very specific segment can be a very painful thing if you don't have a library such as NumPy. And yeah, so what NumPy allows us to do here is to almost like slicing a cake to slicing our data to a specific piece that we really desire. So that is the segment that I would like to cover for NumPy. Is everyone following? Hopefully you are. If you all have any questions, you can always post in the comment section. And yeah, just post in the chat forum. Right now we have Jing Yang and Jet, which is working very hard to answer your questions if you have any. Yeah, so second part we like to cover is actually Pandas. Pandas is another one of these data management tools that is very useful to what we call visualize what the structure of the data so far. So to use Pandas, we will usually write import pandas as PD. That's usually the convention we write. We do this so that even when people hand over our code, so okay, there were people last time ask, so why do I have to write import numpy as MP? Can I write import numpy as MPY? Can I write import pandas as PDAS or something? You can, and it will work if you write PDAS or MPY. It doesn't affect your code processes because because Python itself actually recognizes command as, hey, I want to replace pandas as PDA. I want to replace writing numpy as MPY. Python will actually allow this code to run through if you replace the name as PDA, MPY. The biggest problem with them is when you're collaborating with another partner data scientist. This happens a lot, as in usually data collaboration happens in a large extent. People are always working with each other means that we need to have certain form of conventions, we need to have certain form of things that we agree upon. And importing pandas as PD, importing numpy as MP is part of this convention. We sort of came to consensus that whenever we take over someone's project, um, usually we already assume that pandas and numpy has already been imported for us. We usually do not type this code in anymore. And when doing so, we also assume, along with this, that we already initialized this, and we're using MP for NumPy and PD for Pandas. So this is a usual working convention. So it's very useful that it's very useful for us and for everyone who is interested in data science to understand this convention. So in the future, when you're working together with other people, it's easier for them. Yeah. So that was a bit of a sidetrack, but yeah. Uh, to continue with Pandas, Pandas is like what they said, a very useful package to store and to visualize, to look at the shape of your data, like an Excel sheet here. To actually store and to actually inspect. So for those of you who are very familiar with R, R itself has actually a lot of very useful libraries to do with data science. In fact, it's one of the most favorite data processing software for NUS data science. But what Pandas do is that it takes that same feature and create a data frame. A data frame very much looks like a Excel sheet, except I think it's prettier, and you can perform a lot of operations, such as dropping a row, dropping a column, um, deleting it, imputing, replacing columns, replacing items. These are all operations that are available on Pandas. They are not available on Excel itself. So that's a motivation for you to use Pandas instead of just replacing data in a CSV in the Excel CSV. Yeah. So we can always create a pandas data frame in a dictionary. Sorry, from a dictionary. So dictionaries are, just to recall, a set of data pairs. So a pair that comes with a key and a value. So a key is the thing that you call from a dictionary to retrieve the value. This is a bit of a recall from no, sorry, from the first workshop series. So the moment you call a dictionary and you call in the key, what is going to return you is that we're going to return you the set of values that is associated with the key. So as you can see, this is the we're storing this set of um, we're storing this set of data, which is a dictionary, into this variable we call data. And so we're looking at this with a bunch of state names, putting it into a set of states, and the set of years into a year and the number of population. So from there we can understand that data frame. So we can store this as a data frame, and we store this in a Panda data frame and we name it as data frame. So the moment we print out df, this is going to be the shape. This is going to be the data frame that's going to return us. So for instance, let's say we want to rename our rows. Usually, like they say, usually it's not necessary because we usually we usually want to work with the indexes, or rather this index is already in the Python format, so this itself is good enough for us. But sometimes people may want to have an association with different kind of categories and everything, so you can actually rename it, and the command itself is rename, and internally the parameter should be index equals to, and the index value and the index parameter takes in a dictionary in the form of different data pairs. So so for instance, for those of you who are not very familiar, or rather is still getting used to the index of counting from 0, you can place this into first, second, third, fourth, fifth, and sixth. In place just means that we are replacing this in the actual place of the original 0, 1 to 5. So from here onwards, we can use info. So the df.info is essentially the same as trying to get a summary into R. So we can use the info method to get a number on the number of null entries and everything. So from here, because we ran the df.info column, we can see that there are 6 non-null objects. Non-null objects basically means that the entry itself is not empty. So this is especially important when you are dealing with a large set of data. Sometimes you have a state of how many let's say we are dealing with 1000 rows, and suddenly we throw the data into it and we see that there's 1000 non-null object on state, non-null object on year, but then suddenly we see that there's like 900 non-null object on population. That's how we know that we kind of have certain missing values in population. Yeah, so dataframe.info already gives you a glimpse of maybe you already have missing values, you have things that you need to impute, you already have things you need to start to figure out what you're doing. And maybe sometimes it requires to go back to step 2, which is collection. So sometimes we can this actually is a format that's propped over from using the .describe. So .describe allows you to see a summary of the statistics and variables. Oh, sorry, it's not summary. This is similar as the head function in R. So what it allows us to see is first few entries within a data set. Yeah. So yeah, so like I said, this is one of the ways to see whether you have any data that does not make sense. For instance, sometimes like your age numbers cannot be negative, your district numbers cannot be 5 digits for if you're living in Singapore. Yeah, so if you're and your maybe if you're running with coordinates, your coordinates cannot exceed a certain number. This is always the way to find out that whether your data is within the region, is in place, is correct. Yeah. So there are very few basic functions to access values. So these are the ways that we usually take out certain values. df.ilog stands for dataframe.indexLocate. So it basically means I want to locate a certain entry by their index. So the moment I put df.ilog, rows and columns is essentially what it is. You take the specific row and the specific column. This is quite similar towards NumPy, so we're not going to cover much here. Yep. Okay, so df.log was one of the reasons why we want to rename our rows or columns. So if you remember what we did is we renamed our data frame rows. So this is where it comes in really useful, because by doing df.log, we are referring to the name of the row and column instead of its index. So now we can actually access by second, and the specific name of the row index is a specific name of the columns and rows, instead of using our old methods of indexing, which can be quite annoying if we are trying to count. Yep. So the basic splicing code to get a subset of data is pretty similar to the way we deal with a list or any form of NumPy arrays. It is essentially we're trying to get so we're only, let's say we want to get a first only a few columns, maybe state and year. So we can always put want to find data frame with what do we need, which columns do we need is essentially state and year. And data frame dot 02 is basically first two rows. So these are quite similar to compared to NumPy when you're dealing with when we're dealing with a matrix. So think of it as slicing a cake again, except that this cake is a lot larger because it's usually a data frame which consists of thousands of entries. Yep. So df state, and basically is I'm looking at df my data frame. I want to look at all the state columns, and please tell me how many values I have. So for this one, if we look at value counts, hold on, let me see, does it work? So because we failed to run the previous few data frames, all this code doesn't work. But what I can do is I can start to run this. Okay, so once this is defined and we have to rename our okay, we have to rename our index as well. So all our rename index actually works, and we can actually come down to here. Yeah. So what this does is it shows us how many of these, how many within states we're counting how many. Give me a category breakdown. That means how many do I have that is in Ohio? How many do I have is in Nevada? So what this does is, what Panda does here is they take in every single, they take one entry and look at the actual value, and they'll count how many values of this type there are and how many values of that type there are. This is also a good chance for you to spot if there's any typo within your if there's any big typos in your entries, because sometimes when you're doing data entry, some people may have missed a key or anything, and this will reflect very significantly if you have a large set of data. When you have one set that says Nevada and the other set that says Nevada with maybe a U or something, yeah, this is a very good chance to find out whether there's any small errors within your data entry. Yep. So Boolean indexing. Boolean indexing essentially means that you're looking for certain conditions. So let's say that I'm having my data frame, and within here, let's say the data frame population is larger than 2.0. So remember when we had our when we had our initial data setting, we had a dictionary with a population that states the number of population within the state. And this is very useful because when we access this column, we're essentially telling Pandas that, look, I want my data frame. So I want my data frame that's I want to look at my data frame. And in this data frame, I want to access the population column. And the column, if the column index, or rather the column value is larger than 2.0, return this to me. So this is when we can use that. So the reason why we have to put another df unlike the other ones is because this df pop allows us to act is a way for us to call the population column within our data frame. And from this call, we access every single column in the data frame that has to do with population. So this is actually one set of data in itself. The other set of data, the other set of df, this outer df, is actually telling them, please return me the output as a data frame. So this data frame is a column, the column that is larger than 2.0, and this is, please return me the output as a data frame. Alright, so everyone gets? Alright, thank you. And From here onwards, we can do some, once again, we can do some vectorized operation. That's quite similar as the NumPy. Yes. So df.pop plus equals to 1.0 is essentially, please take every single population entry and add 1.0 to it. And the addition of 1.0 to only the pop of the row with row name 2. So this is essentially, this part has a lock, third, and pop side. This is your old lock function, which is the slicing. So this slice out any part that, this slice out the third row population, which is basically the third row population column, and added 1.0 to it. So once we are able to do that, you can see that now our DF now has everything actually is one increase from the previous one. And because of, and from the second part, we can see that we added another 1.0 to the third row population column. So this was 5.6, where originally it was 4.6. Alright, so let's talk about dataset. Okay, so sometimes after we ran our data collection, we may have it stored in our own system, but most of the time we're not usually storing our own system. We usually get from any other external sources, and that's when downloading dataset counts. So usually we will download from Kaggle. It's actually quite common. Hold on a moment. Okay, so we'll go to data. So we can always have any data set that you want. If I'm not wrong, we took one of them from California. Oops, hold on. Yeah, so it's California housing prices. So this is where we get our data from. Kaggle. Yeah, go look it up. Kaggle is a pretty good website, I guess, for dataset, for learning about data science, and to also generally, there are also competitions involved if you are interested. But another one I would like to show you is actually a Google dataset that has been actually um, there's been out for quite a while. Actually, no, it's just quite recent. I'm so sorry. So Google dataset allows you to search for any dataset that you are interested in, and some of them actually goes back to Kaggle, as you can see here. Yeah, so they actually state their sources, and all of them, some of them are pretty good. Like data.ca.government, this is actually a government website. They uploaded their data towards this site. Yeah, and like you can see, a lot of them actually comes from Kaggle, because Kaggle is one of the bigger names out there in data science. Alright, so that is that sidetrack. Alright, so usually we run this whole chunk is basically our way of downloading a dataset. You all really don't have to learn this for now, I guess. Yeah. Yeah. So so we'll talk about data sets. Yeah. So once again, this set of import warnings and everything is us importing a bunch of libraries that involves a lot of involve a lot of exceptions. So this is not really required as well. So for now, we'll take a break, and after that, we'll come back to do EDA, which is we'll plot our graphs. We'll plot our data within certain data graphs, and that is within data visualization. All right, see you all in about 5 minutes, 7:35 maybe. All right.
Done. Can mute in case the video goes background. Okay, let's pause this one just in case. Sorry? Let's pause this one just in case. Oh, I thought you were doing that. Hi, can everybody hear me? Can y'all hear me? Because Hi, so for this second part, we will be looking at exploring our data and also pre-processing our data. So the data we have here is the California housing data set. The point of this data set, which we will cover in the next workshop, is also to we want to put it into our machine learning model. So we want to predict the median house value of a house in a given area. So for data visualizations, there are a few libraries out there that is able to do data visualization. But for this workshop, we'll be looking at Matplotlib. So basically it's just a library. There are seaborn and other stuff. So how you import Matplotlib is basically Matplotlib, import matplotlib.pyplot as plt. So that's the convention. And we will import NumPy and Pandas also because that's how we are going to use it to manipulate our data, look at our data before we put it into our model. So let us go to the code first. So some functions that we will usually use, as also described by Michael just now, like data.shape, data.describe, and data.info. So the code is ran here. So specifically, let's look at data.info, right, which is my third command, which will output me this chunk. So you can see that we have like longitude, latitude, things like that. So these are the features, these are the columns we have. So specifically, we can see that for the total bedrooms column, it has 20,433 values, whereas we have 20,640 entries. So this means that there are some missing values, like 207 missing values over here. Then for the rest, it seems okay. And also we look at, we see that most of our columns are numeric columns, like it says float 64. And for ocean proximity is actually a categorical variable, which we will look at later. So 20,640 and 10 columns, missing values. So we see that ocean proximity is object. It says object here. So we can run this command and we see that it's like a categorical variable with 5 kinds of possible values. So basically we kind of look at our data already. So we can see that there's missing values and things like that. So we will need to do some cleaning of data. And usually when we do that, we look at if we have missing values and if we have duplicate rows or columns. Usually we won't have duplicated columns, but duplicate rows might be there. So this first command, it tells you, so data.isNA bracket, right, it will just return you a kind of a table of trues and false, and when you sum it up, it will sum. So basically, if there's NA, it will return true, and you sum up all of the isNA, so you kind of like you get how many missing values there are. So basically it says 207 here for total bedrooms, which is what we kind of speculated just now. The rest are zeros. So there's 207 missing values for this column. Then we check if there are duplicated rows and duplicated columns, which you see my output here is 0 and 0. So there's no duplicated rows or columns for this data set. But if there is, this is a command to check. So basically data.duplicated is to check if there are duplicated rows. So if you want to check duplicated columns, we do a transpose, then we .duplicated it. So if there's duplicated rows or columns, we can just use this command to drop all the duplicated rows and columns. But in this case, even if I run it, it will return me the same thing because there's no duplicated rows or columns. So for the missing values, right, mainly we'll look at there are three ways to sort of deal with it. So it's either we remove the rows, or remove the rows that has the missing values, or remove the entire column, total bedrooms, or we impute the missing values, which is basically we fill it up with something, which I'll talk about more later. So for the first two rows, the code is here. So sometimes we run method 1, but in this case we are going to try imputing later, so we'll not run it here. But the command is basically we check where in the table the values is missing, is NA. Then if it's false, then we retain it, else we just throw it away. So second one is remove the columns. Usually you don't do that unless you see that the columns, majority, maybe more than 70% of the rows have missing values in that column. Then maybe we think that the column is quite useless, so we just throw it away . So for this case, we have 20,000 fields and there's 200, which is 1% missing value. So obviously we don't drop the column. So yeah, usually we'll use method 3. So we'll do it later. So we'll do some data visualization now. Maybe we can look at the slides. This graph seems nicer. So basically, this is a histogram of our 10 columns. So 9 of these columns are numeric, so it's a histogram here. Here is just a bar plot . So you can see that it's kind of strange for 2 of these 9 distributions. So you can see that, you see housing median age. At the end, there's a sudden spike, even though it shouldn't be the case. And for median house value, it's even more obvious that it's kind of going down as the median house value increases, but it suddenly spikes at 500,000. So yeah, there's something weird going on there. So that's why we are doing data exploration, so we can see where are the anomalies and outliers, and like I mentioned previously, missing values or duplicated rows and columns before we put it into our machine learning model, because we don't want to put in faulty kind of data, because it will not help us in our predictions. So there's also this kind of different visualizations. So for the visualization on the left, you can see that there's some strong relationship between these respective features. So specifically, we want to look at median house value, right? Because next workshop, we want to use our machine learning models to kind of predict what's the median house value given a set of features, the other 9 features. So it seems like what's correlated with median house value is median income seems to have quite a big impact on a house value. So these are the stuff we can glean based on our data exploration. And also you can see this plot on the right where there's median income against median house value against median income. So you kind of see the trend, like if a median income is higher, the median house value, median income of the people working there is higher, the median house value kind of increases. And there's this price cap at the top, right, which is strange, but it's also because our median house value, there's a cap. As you can see, the median house value, there's a strange spike over here, so that kind of explains that. Yeah, so maybe we can look at our code. So here I am at my notebook. We do import matplotlib.pyplot as plt. Then we kind of do plt.style.use cbond. So basically it's just a stylistic thing. For example, if I remove this, then I run this, then I run the next one, data.his. So basically for my 9 numeric columns, right, it will just plot histograms . So the bins, we have 50 bins. Yeah. Oh, wait. Yeah, okay. So yeah. Okay, never mind, it's not. Okay, so basically this is what is shown on the slides. Yeah, so housing median age and median house value, there's some weird spike at the very tail. So let us just look at housing median age. So I specifically spliced the data set to give me just this column, and I plot out a histogram, which gives me this. So I can take a more closer look because on top is a bit small. So we can see, like, you see around 50, 51 kind of, we only have like 200, roughly 200. But suddenly at like kind of 52, it spikes up to so high. And I'm just running this code. So like this is where your NumPy and Pandas kind of basic knowledge comes in. So we splice our code, and for the values where it's equals to 52, we sum it up. We have 1,273 of such values. So that's very weird, right? Because for example, you look at 51, we only have 48. Then 50, we only have 136. So it suddenly goes up. So for that, we can do things depending on the context of your data set. Sometimes you have to know how the data is collected, and possibly this could not be a mistake, but it very well could be also. So it depends on the context basically. So if you know that this is a mistake and you want to remove it, how do you do that? So basically you just do some splicing where the value is not equals to 52, you keep it, then you reset the index So see, after doing that, I removed the 1,273 rows. So initially I had 20,000, so now I'm left with like 19,000. So this is just some code you can use to remove things like that. Yeah, so in this case we won't remove it, but it depends So this is another plot we have, which is just kind of cool that we want to share with you. So when you plot the latitude against the longitude, it's kind of like the coordinates, right? The geographic coordinates. So you see that houses are strangely, they are kind of like interspersed in a relatively straight line kind of thing. And we have this plot which is more complicated. You can examine the code later, but basically what we are trying to do. So for this first plot, kind of we just introduce like 2 dimensions into our plot, which is longitude and latitude. But for this plot, you see that there's a population size. So a bigger a population size, the bigger the circle, as you can see by different you can see by different points with different sizes. And also median house value is kind of like heat map. So you can see that around this area there's kind of bigger circles, so like there's greater population there and it's very concentrated. And also median house value is kind of high because it's going towards the red orange-ish. So like this is like kind of a popular spot, and I guess this is also relatively popular, whereas there's other places with very small dots and less dense, and also the color is darker, is colder, with a lower median house value. So that's just a plot which so we can also look at so some attributes to plot a 2D scatter plot. So for this specifically, we use Pandas dot plotting. We import scatter matrix. So on the diagonal right is basically, like for example, this bottom right corner is housing median against housing median. That's why it's a histogram. But for the rest are all scatter plots so it just kind of gives you an idea. Like this is the plot that we see on the slides earlier, median house value against median income. So as the median income kind of increases, median house value tends to be higher. So this is that. Okay, so basically we kind of like visualize our data and sort of clean our data by removing duplicated columns with duplicated rows, kind of filling in and dealing with missing values. And also we look at our plots to see like kind of anomalies and things like that, which can be removed depending on your context. So later we are going to see more about how we can replace missing values, because just now I kind of only talked about removing the entries, right? So how do we fill it up, and how do we deal with categorical features? Because in machine learning models, we look at our data in terms of numbers, right? Machine learning models are just like statistical tools, kind of, to playing with numbers. So if we have categorical features, they are like strings, they are not really numbers. How do you deal with it? And looking at engineering new features, because basically what we put into our models, the features, is what can increase or decrease our predictive powers of our model. So you have to put in, sometimes you have to handcraft some features that better describe our data set and better describe and help us to predict the correct labels or values. And so we will move on to the next part, which is pre-processing the data. So as I said earlier, like kind of to make it better for a machine learning algorithm, and also expose some data patterns. So for this part, we will be using scikit-learn. So those on Jupyter Notebook or kind of on your own terminal, not Google Colab, you can just do a pip install sklearn. So what is this library? So it's a free library for Python. It has like various algorithms like support vector machines, decision trees, things like that, and it's quite closely integrated with like NumPy and SciPy. So basically it's just a very popular machine learning library for Python, and it also does help us do stuff to pre-process the data, which is what we will be using it today for. It will be more formally introduced next workshop by our other speaker Jet, when we talk more about machine learning models. But for now, we will still use it to like kind of pre-process our data. So as I said earlier, the algorithms mostly we can't handle missing values. So it's either like remove the row, remove the column, or impute the values. So missing values, it can come in different forms basically. So you see, sometimes it could be a NaN, like in Python in NumPy they recognize it as a missing value, NaN. So it's not like a string, it's a kind of a null kind of thing. Then sometimes it can also comes in like weird values. So for example, feature 2, I don't know what is it, but maybe you can think of it as temperature, for example. Temperature is 37.8. How can a temperature be negative 999? So things like that, you can see that it's very obviously is a error there. Or things like this, maybe this is a weight, this guy is 52 kg, 41 kg, then there's a minus 1 kg. So these are just ways that there's missing values. So perhaps when the data is collected, our person who collected the data just use -1 as a convention to mean that it's missing, but it's not what we want to put into our machine learning models. So sometimes you have to like look at your data, use your Pandas and NumPy to examine the data and discover weird stuff like this. So like for feature 3, you could have spliced the data set and sum up and set it to a Boolean condition and sum it up. Then you'll know, why are there stuff below 0? So for categorical, there could be missing also, like this is just a string with one white space. So this is wrong. So as I mentioned earlier, I mentioned the first two ways, right, to get rid of the rows. So for example, maybe I could get rid of this row because it has a NaN at a -999. We don't want this row at all. Or we could get rid of the columns. So for this, even for this, of 5 values, there are 2 missing values, right? So actually it's not a lot, but I mean, depending on the application, we could remove the columns, or we could impute them, which is what I'm going to talk more about now. So basically, when you want to impute, so first, remember that we have categorical or numerical values. So for categorical values, it's kind of like this low, high, medium kind of things. So in our data set here, right, we have a categorical categorical column, where is it? Yeah, ocean proximity, right? We have 5 categories, although one is very little lah. But yeah, we have 5 categories here. So for things like that, when we want to impute, if there's a missing value, we could create a new NA category. So like we just kind of say NA, because that could encode some information, right? Because we don't know, so it depends on the context again. But when the data is being collected, sometimes the person collecting it left it as a missing value because, I don't know, maybe there's a reason for it. And across all of these missing rows with missing values, yeah, there's a reason that is NA, or maybe sometimes it's just they forgot to collect it, or it was just a mistake or a typo. But NA could mean something that helps us kind of capture this pattern of like, oh, why does this person always leave a missing value? Or maybe there's some specific pattern going on here. Or we could just put it with a mode. So for numerical values, we have like mean and median, right? But categorical values, there's no mean and no median. So we just put the most common value. So mode just means the most common value in that column. Yeah, so for this case, I guess the mode would be O minus. Yeah, O minus. So for numerical values, we can either put a mean or median to fit into those missing values, or we could also create a new feature that indicates that there's a missing value. So for this fit for is NA, right? It kind of say that we kind of impute for this fit for a missing value, we impute it, but we also indicate in this fit for is NA that is 1, that it was originally NA, but we imputed it. So the others is 0 lah. So basically this could mean something also, as I mentioned earlier about the pattern, like maybe there's a reason that is missing. So this one kind of convey that information, and it's up to the model to kind of learn if this feature is really significant. Yeah. So okay, let's move on to the code. Move back to the code here. So now we are looking at imputing missing values. So this is just a refresher from just now. Yeah, so missing total bedrooms, blah blah blah. Okay, so first let's try to impute the numerical features here. So we have numerical and categorical, right? But yeah, 3.1.1 and 3.1.2. So we are just doing numerical features first. So we use sklearn. We just do from sklearn.impute import simple imputer. So this will just be the command that we will be using, this function. Yeah, so this sklearn package, which yeah, we will be using it more in the next workshop. So this is some basic from what we learned just now again, pandas. So we drop away the only categorical column. So what our data num has left will be the numeric column. I mean numerical columns. Yeah. So just yeah, you see that the ocean proximity is gone lah. Basically, all our remaining stuff in this data frame is all numeric. If you don't do this, you put it into the imputer, it will return you an error, because you see that we initialize our imputer as an object. So simple imputer, we give the argument as median. So our strategy for using this imputer will be median. It could be mean also, but for this case we are just using median. So if we are using this imputer for our original data set with the ocean proximity, there will be an error, because yeah, ocean proximity, there's no median because it's a categorical, it's not numerical. That's why we drop it. So the command is just like num imputer dot fit transform data num, which is the data frame with numeric data frame, and we save it as data num imputed. Okay, so this is just FYI. So data num imputed is a numpy array. So data num imputed, you can see here, is a numpy array, a 2D numpy array. It's not like, even though initially our data num, right, you can see that our data num is a pandas data frame, but after putting it into that sklearn feed function, we only get a numpy array. So yeah, this is just FYI. So even though the values is like the same thing, but the format is a bit different now. So here we just want to confirm that so basically the imputation here, right, we are applying it on the entire data frame with numeric, which is the 9 columns, but actually we are only imputing 1 column, because as you can see here, actually we only have total bedrooms with missing values. The other numerical columns don't have missing values, but basically you just do on the entire data set, so the others will be untouched. So this command, we kind of get the columns. We get the column names actually. Data num is the pandas data frame, right? We put it into a list, so it's a column names. Then this thing is what I have on top, right? This 2D numpy array. So we put it into this pd.data frame, and we specify that the columns are the columns names we have here. So it will give us back the pandas data frame. So it's this stuff, put it into a data frame with all the column names. Then we do .info. So now we can see that the total bedrooms column, there's no more missing fields. It's filled by the median of that total bedrooms column. So we have successfully imputed the data frame, this column specifically, with the median values. So now we are going to look at categorical. So basically, you know that we don't need to do this step because there's no missing categorical variables, but I'm just going to show you. So this is the same as what we are doing on top. So we specify that we are choosing ocean proximity. Then now our simple imputer, our strategy is most frequent. Then we kind of put it through the same kind of code. Then we'll get the results will be the same because there's no missing values. But if there was, this will fill it up. So basically that's how imputation works. So now we are going to look at another part of pre-processing, which is feature encoding. So basically, like I mentioned earlier, our algorithms deal with numbers, not categorical features, kind of strings, weird kind of factors kind of thing. So we need to represent this in a meaningful way such that there's still information contained, which is why this is called feature encoding, for our machine learning model to learn something. So basically one way, like you can see here, maybe we just change it to numbers directly. Like maybe we just choose this as 1, this is 2, this is 3, whatever. Then maybe low is 1, medium is 2, kind of thing. So, but before that, we just look at the different data types. So on the far left is numerical variables, which are our 9 columns earlier. So this is not categorical, of course. So like weight A is 40, weight B is 88. We can see that there's like a continuous kind of, there's numbers to it, it's quantifiable. So you can say specifically that weight B is 48 more than weight A. Whereas these 2 rows, right, we are going to look at these 2. They are categorical variables, but even within categorical variables, we can call them, subdivide them into ordinal or nominal, right? So you see ordinal, there's some kind of order to it. So maybe you're buying a Starbucks drink. You can see that tall is more than short, grande is more than tall, venti is the largest. So there's some kind of order to it. That's why ordinal order. Whereas nominal, there's really no kind of order. You can't really say like water is better than milk or what, or unless you're there's no order. It's just a kind of preference thing. So like you see ordinal, you can, if you want to say which is the largest, there's a specific kind of which is the largest. For this kind of water, milk, coffee, soda is, if you're looking at like kind of taste, right, which tastes the best is kind of, there's no order to it depends. So that's nominal. But the difference between ordinal and numerical is also that, yeah, we can't really quantify a difference because, I mean, yeah, you can't. So, yeah, so the ordinal and nominal categorical variables, so it also affects our approach to how we encode them. So for ordinal, we can encode them, since there's some inherent ordering, right? We can choose like low to be 0, medium to be 1, high to be 2. Yeah, because medium is higher than low, high is higher than medium. So 0, 1, 2. However, this also kind of give us it feels like there's some kind of distance involved, right? Because you see that now medium and low, the difference is exactly 1. High and medium, the difference is 1 also. So are you saying that the difference between medium and low is the same as the difference between high and medium? So this is not necessarily the case. We don't know that actually because it's not a numerical variable. So this kind of distance, it induces some kind of distance which may not really be good sometimes, but sometimes it's fine, then we can just do it this way. But if you know that yeah, the differences between each category is not really the same, then this might not be too good. So another kind we can look at is one-hot encoding, which can be applied for ordinal variables as well. But if you do that for ordinal variables, you lose the order, the kind of ordering. But it's especially useful for nominal values. And yeah, remember nominal values means there's no order. So basically, we just kind of spread the values out, right? So we have 4 different values. Now we have 4 different columns. 1 just means for this row, right? If it's 1 here, it just means, yeah, the blood type was O minus. So it's like, this is called indicator features, right? And in some different fields, they call it differently, like dummy variables or indicator variables or whatever. So yeah, so there's kind of, if we have a 1 here, the others will be 0 lah. So that's, I think it's quite simple. So there's no implied relationship between them. Yeah, like you don't know, we are not talking about ordering here. There's no order here. So it's just 1, 0, 1, 0. Yeah, so okay, let's move on back to our code. So in 3.2 here, right, we are looking at our categorical variable, ocean proximity. So we have these 5 variables. So we can't feed this column into our machine learning model just as it is. So we'll do some pre-processing. So again, we are using sklearn. Sorry, yeah. Let me drink some water. Yeah, so we are using scikit-learn here. We use one-hot encoder, which is what I talked about here. I will not be using ordinal encoding here in this session because as you can see from our data set here, right, there's no inherent ordering, although yeah, different people might prefer different things. So we can't really, I mean, we can't really say that one thing is better, one kind of ocean proximity is more beneficial, like maybe to our median house value. We don't really know that. So to be safe, we just do a one-hot encoding, which is what you see here. So the code to do that is, yeah, basically we import one-hot encoder. Then we create this object again using this function. So it's kind of similar to the imputing thing we did just now. So we .fit transform on this object and we feed in data cat imputed. So basically, if you recall just now, right, our data cat imputed is just, oops. Yeah, basically it's just this numpy array of the categorical features. So yeah, so this doesn't have order numeric lah. So you just put this categorical numpy array thing inside. it will return you data cat encoded. So what's data cat encoded, right? So now we see that basically this is like what we have just now. Like you can see each row there's only one. Yeah, each row only has one. So there's 5 stuff, right? Why 5? Why do we have 5 columns? It's because we have 5 kinds of values. So we get a 2D numpy array. So like previously we do this one hot dot categories underscore 0. So it gives us the column names. Then we make the data frame again. We feed the column names in and we put in this 2D numpy array. Then we just do a dot head just for you to see. So yeah, you can see this is what we get after we transform the stuff. Yeah, so okay, let's move to feature engineering. So what we want to do here is, as I mentioned just now, we want to put in features that are meaningful, right? Because sometimes we have lousy features that will kind of taint our predictive models. There's too much noisy data, which is not helpful to our model in trying to learn the patterns and trying to basically learn the patterns, then subsequently predict stuff. So what we want to do here is create better features here. So how do you do that? You need to have some prior knowledge, like domain knowledge. So maybe you are very well versed in housing prices. So like you kind of know that what kind of features are important, what kind of features can affect the prices of a house. So so knowing that, maybe you'll be like, the features I have in this data set is not enough, or I need to modify it such that it gives me the correct features that in my own experience I know that it usually affects our housing prices. Or alternatively, if your EDA is done well, you can sometimes see some patterns, and based on that you want to make some features to help you put into the model. So for this case, we see that basically we have total rooms in our data set and households in our data set, right? So basically each row in our data set represents an area, a district kind of thing. So that's why we can have 3,000 total rooms. It's not like one house has 3,000 total rooms. It's like this area, this longitude and latitude, there's X number of houses, there's 675 houses, and total there's 3,000 rooms. So obviously if there's more households, there are more rooms, right? So you can see here there's 600 households, there's 3,000 rooms. There's less than 200 households, there's obviously going to be much lesser rooms. But we can kind of use this to create a rooms per household thing. So in fact, you see it's funny, right? The last row, right, there's more rooms per household compared to the second last row. Even though if you don't do this feature engineering thing, on first glance you might think, oh, this area, right, has more rooms than this area, so that's why the prices are higher. But that's not true, because actually you see the rooms per household is lower. So in fact, maybe it's more likely to have a lower house value, even though total rooms are higher. So you kind of, this, I guess it's just overlooked sometimes, but when you think about it, it makes a lot of sense that you see rooms per household, we are not just looking at the absolute number. So on the right is population per household. So maybe some people like areas with lower number of people living in it, less densely populated, so the house prices might increase. So it's more about density rather than the absolute number. So yeah, these are just ways we can engineer our features. So it also depends on context. So okay, let us look at the code again. So for our first part, we are going to do np.columnStack, right? Yeah, you can even see what's the description of this function here. take a sequence of 1D arrays and stack them as columns to make a single 2D array. So we have data num imputed, which is the pandas data frame we have just now, where we imputed the missing values in total bedrooms. Then we stack it with data cat encoded, which is this thing here. So we put it together. But when we do this command, right, it will just return us some 2D array again. So for 2D array, we want to present it in a nicer pandas data frame. So we just put it into this command again. The column names we just put this is what we have just now and this is what we have just now. Yeah, so basically you just run this command. Now your final data set that you are ready to put into the model is data preprocessed. So we have longitude, all this nicely. Everything is in numbers now. There's no categorical features. I mean there is, but it's represented as numbers now. And we have no missing values, we have no duplicated values, we have no missing rows, no duplicated rows. Yeah, so it's ready for the model. And as I mentioned just now, we can just run this code. So we are looking at total rooms divided by number of households, and we are going to call it rooms per household. That's our new feature. So I run this code, and yeah, I can see this new column at the last. This wasn't there before. So rooms per household. Yeah. So now we have this engineered feature lah. So once after this, basically our next step will be to fit into our machine learning models, right? So we can look at how our median house values is affected by all these other features, all these other conditions. Yeah, so yeah, basically that's it for our workshop 3. So for our next workshop, we'll be doing on our machine learning models, right? So we'll be looking at some machine learning models like linear regression, logistic regression, things like that, to kind of do some predictions. Then we'll look at how good our prediction is, how accurate it is, how many true positives kind of it gives us, and things like that. So that will be our next workshop, where we'll be using this data and this clean and pre-processed data for that. So thank you for listening, and may I ask for everybody to go to this link to do a feedback, so that we can learn a bit of how the workshop was today for you all, and give us some feedback and suggestions if you have any. And yeah, is there anything else? Yeah, so I guess that's it. Yeah, we'll be reading the comments, so if you all have any comments, you can comment on this YouTube chat now. We'll be around for a while. You all can just comment, then if there's anything you all want us to share, we can share. And yeah, also do the feedback lah. Yeah, okay, thank you everybody. Hi everybody. So yeah, our next workshop on machine learning models and evaluation will be in week 8, which is 3 weeks from now. So yeah, basically until then, y'all can kind of leave your feedback and tell us if there's any specific things you want us to go through, or yeah, 3 weeks. It will be online as well, I think. Yeah, so yeah. Yeah, so I think most people have left already, but for those who are around, yeah, maybe just help us fill in the feedback form, and thank you for coming e-meeting. So yeah, that's it. All the best for your recess week, I guess. Okay, thank you. Bye bye.